Chapter 4, Section 3, Applications of Matrices to Data Science. Matrices can be used to streamline various calculations in data analytics. If we store our data in matrix format, we can perform efficient calculations using Python's NumPy and Pandas libraries. In addition to their use in programming, matrices can also streamline various operations in data analytics due to their mathematical properties. As examples, this section will look at linear regression and calculating the distance between data points. First, let's see an example of our use of matrix operations in linear regression. Let's consider a linear regression model with three predictor variables. In a linear regression model, the predicted values are expressed by these equations. Here, y is the predicted value. x1, x2, and x3 are predictor variables. Beta 0 is the intercept, and beta 1, beta 2, and beta 3 are the coefficients of each predictor variables. A coefficient represents the impact of a predictor variable, so it is also called a weight. Suppose we want to compute predicted values for this dataset. It consists of 4 samples and 3 predictor variables, x1, x2, x3. Each sample has its value for x1, x2, and x3. We can define a feature matrix of this dataset. Each row represents each sample. All elements of the first column are 1. This column represents the intercept. Other columns represent each predictor variable, feature. So, this feature matrix represents a dataset consists of 4 samples, 3 features, and intercept. And we can define a weight matrix. It has only one column, so it can be also called a weight vector. The first elements represent the intercept, and other elements represent the coefficient of each predictor variables. We can compute the predicted values y for each sample by multiplying the feature matrix with the weight matrix. Each element of the resulting matrix represents each sample's predicted value. We can see that each element represents the linear regression equation. So, matrix multiplication using feature matrix and weight matrix enables us to efficiently compute the predicted values for a linear regression model. Next, let's see an example with specific values. Suppose this linear regression model can express the relationship between y and predictor variables. This dataset is to be used here. We can define a feature matrix and a weight matrix from this dataset and a linear regression model as shown here. In this case, the predicted values y are calculated as follows. In this way, by including the intercept in the matrix calculations, the predicted values for multiple samples can be efficiently computed all at once. Using matrix operations allow for the fast processing of large datasets, enabling efficient predictions. Next, let's see the benefit of using matrices and matrix operations to compute distances between data points. Suppose we have these 3 data points. We want to compute distance between these data points using Euclidean distance. We can compute Euclidean distance between A and B using this formula. But here we have 3 data points. So, if we calculate distances for all pairs of data points, we need to repeat the same calculations 3 times. If we have more data points, the number of repetitions will exponentially increase. It is inefficient, isn't it? Using matrix operations, we can calculate all the distances at once. To apply matrix multiplication for calculating distances, we start with these three data points as this matrix. Each row of matrix X represents each data point, and each column represents each feature. The first row represents data point A. The second row represents data point B. The third row represents data point C. The first column represents the x-coordinate, and the second column represents the y-coordinate. Let's create a matrix which consists of the sum of the squares of each element in each row vector in this way. Let's call this matrix as large S. Using this matrix and the original matrix X, we can create a distance matrix, which displays the Euclidean distance between each pair of data points. We can obtain the distance matrix using this formula. By plugging in each matrix and its transpose, we can implement matrix operations in this way. It is a little complex, but we can do it if we do it carefully. The resulting matrix is the distance matrix. We can see that each element represents the square of the Euclidean distance between two data points. For example, the element in the second row, first column, represents the square of distance between data points A and B. The element in the third row, first column, represents the square of distance between data points A and C. All diagonal elements are zero, meaning that they represent the distance between the same data points. So they are all zero. Let's go back to the concrete example. The matrix X and the matrix large S can be expressed in this way. So let's obtain the distance matrix using these matrices and matrix operation. We can obtain the distance matrix in this way. We should know that the distance matrix shows the square of the Euclidean distance between the data points. So we need to compute the square root to know the distance. In this way, we can obtain distance, the information of similarity between all pairs of data points at once. We can apply the same method even though the dataset contains more data points and more features. Matrices and matrix operation enable us to implement these calculations efficiently. Thank you for watching. Please thumbs up and subscribe to my channel.